So look, let's see. Hemizygous genotypes. All of the ones with the hyphen or the dash. Hemizygous means half zygous. It means you only got, you're diploid, but you only have one copy of the chromosome or one copy of that gene. So good. Yep, that represents a lot of answers that were B and D. X, Y, and ZW individuals develop as males. No. False. So, yeah, most of you got that, a third of the class. And so I'm assuming then that if we, let's see, so I'll go ahead and, I'll let you work on that for a little while longer if you want to before I close that quiz. So, yeah, questions then.
Because from the XYZ and the ZW, will we discuss the genetic implications of gender, with other more temperature dependent versus?
I'm hoping you may not remember. At the end of the semester, I left a few days open for to be announced topics. So if anybody has any topics that have come up over this semester that you want to talk about, like sex determination and the difference between environmental influences and genetic influences, I'm certainly happy to do that. But you're absolutely right. So especially given global warming and the fact that a lot of animal species have sex that's determined by temperature that their eggs incubate at, it could be a big problem for especially reptiles and amphibians. If the world warms and all of a sudden one species' eggs are all incubating at hotter than normal temperatures, all of the individuals in that species develop as either males or females, what happens? Extinction, right? You've got no one to mate with. Unless you evolve hermaphroditism, which takes a long time to do. So.
Parthenogenesis, I think, is also.
Or parthenogenesis, yeah. Clonal reproduction. Any other questions about those topics? It was just from the movie Hemizygosity. So which individuals in birds, Lepidoptera, moths, butterflies, and others, which sex develops as males? Which chromosomes? ZZ. I want to make a ZZ Top reference, but I'll just not bother at this point. Okay. So today is completely open for question and answer. I've popped a lot of examples in here that we can go over. Happy to answer questions as always, but if anybody has any questions on anything we've covered up until this point, especially pedigree related, we're going to do that. What I've developed for today, in case we get that far, is some examples of pedigrees, working through pedigree analysis, and also a little bit of including how to use chi-square analysis to help decide on inheritance patterns. So that's where we're headed today, unless I get distracted by excellent and insightful questions from you. Anything yet? All right.
Maybe we can go over this pattern, inheritance pattern one.
Yeah, so this is a good combination of pedigree analysis and phenotype mapping. So this whole purpose of this slide, quick little mini lecture, is to review allele nomenclature for short repeats or for microsatellites. So if you've got an individual that has CG reading from 5' to 3' down that left-hand strand, then we call that a what allele? What's the shorthand for that? CG2. There's 2 copies of CG. So that's a CG2 allele. And down here on the bottom, we've got 1 copy of a chromosome in a diploid organism has 4 T's in a row, so that's a T4 allele. And the other chromosome that this person inherited from their other parent only has 3 T's in a row at that spot, so that's a T3. 3 T's in a row. Okay. Should be a review, pretty straightforward. So the question on this slide is fill in the blanks. We've got a pedigree here. So this is just like some examples we've done before. What can we tell about the genotypes of individuals based on in this case, working from the parents to the offspring. Can we be sure what genotypes are going to go in those two blanks and in that blank? So if daughter 2A got a CG3, where did it come from? One A or 1B? Or 1B, right? CG3 is present both in the mom and in the dad. So we don't know which parent, just by itself, just with that information, we don't know which parent that chromosome came from. Unless, so we've got a haplotype here, CG3 and T4 together. So it could be that that whole thing, that entire haplotype got inherited by daughter 2A from her mom. What has to be true for that to be true? No recombination between them. If recombination happened between the CG3 and the T4, then that mom would be passing down CG3 alleles that were coupled with T3. So in the absence of not giving you any information about recombination, that is how far apart on the chromosome those two markers are, we're back at the first situation, where we don't know which parent the CG3 came from. But yes, if those two, if the CG3 and the T4 were really close together on the same chromosome, like perfectly linked, 0 centimorgans apart, then you could say, sure, that haplotype, that combination of genotypes or alleles was present in the mom. It's most likely that she was the one that passed that combination on to her daughter. So if that's true, then what do we know about her other chromosome? So if it's true that her mom gave her both of those alleles, like drawn here, what would we fill in over here from the dad?
We know for sure that it's T3.
Right, so dad's homozygous for T3. So we know for sure that there'd be a T3 there, but we don't know which of his CG alleles, 3 or 4, he would pass down to his daughter. What about the third blank in son 2B? Can we figure that out in any way?
We can assume T3 if there's no recombination.
So this, right, the CG2 that he has had to come from his mom. There's only one CG2 in the parents. So it would either come with a T3 or a T4, depending on whether or not there was recombination. So that's either T3 or T4. And again, if this was on an exam, I'm happy for you to pick one as long as you explain your reasoning. So you say, if there's no recombination between those two alleles, CG2 and T3, then that CG2 would be inherited with a T3. If there was recombination, then the CG2 would go together with the T4 into the offspring. That's fine. Pick one. Say what it is you're using, your mental information, to make that decision. Shows your understanding of the material. Further questions, comments, concerns?
So if we were gonna get this on an exam, a question mark is perfectly acceptable for that first.
Question marks are never perfectly acceptable. An answer is acceptable as long as you justify it. So you can put in either one of those. The question mark represents either one could be correct. You still have to justify why you chose it. Yeah.
Looking at 2C, we know that there was a recombination there.
Ooh.
Because we know that if we would say that CG3T3 comes from dad, then we would say that the other comes from mom.
Oh, so let's see. Individual 2C. Back up just a second. We've got a CG4 Which parent did that come from? Had to come from dad. So do we have any information about whether or not recombination happened in dad? What's the genotype down below? It's T3 over T3. So if dad provided that CG4, he's homozygous for T3. So you're absolutely sure that regardless of whether or not recombination happened, he passes a T3 on to that individual. Okay, so we don't have any information about recombination from dad, but what about mom?
So the mom, we have CG3, and we're expecting the other T3 to come from mom, and that CG3 only goes to T4, so then it has to be a recombination.
Right.
And my question is, after we know that one of the siblings have recombination, do we expect that the other two also went through recombination? Then our answers will be correct, or is it like independent?
Excellent question. So if you know that recombination happened between two genes in one parent, I'm paraphrasing, if recombination happened between two genes in one parent, do you know anything about whether or not it happened to happen in the one gamete that fertilized that individual that came from the other parent?
I would expect to say no, like independent from each other.
Yes, you're right. Independent from each other, no, you don't know for sure. The only thing you would know if you observe recombination in one parent is something that's sort of qualitative. You know at least those two alleles or genes are far enough apart that recombination can happen between them. So if you saw a recombination like this, and then you said, in the other parent, you said, oh, it has to be this combination of alleles because recombination might not occur between them because they're so close together, then I'd say, wait a second, but recombination happened in the other parent. So you can't argue that the second parent, those genes are perfectly linked. They're so close together that recombination could never happen between them. That would be you arguing against yourself. But you're absolutely right. In this case, you can tell something about recombination. Yeah?
And would it be valid to say just assuming recombination just doesn't occur, even though it could be possible if we assume it doesn't occur, it could be this haplotype?
You're welcome to state that as an assumption. Yep, that's what I'm saying. So if you want to pick a situation, if I don't give you information like a genetic distance, you are certainly welcome to make one up. Say, I'm assuming that the genetic distance between these two alleles is 50 centimorgans. That's fine. Yeah.
What's the genetic distance, like, cutoff point when you don't expect recombination to occur?
I'll let somebody else answer that. How far apart would two genes have to be for you to be unsure whether or not recombination would never happen?
50 centimorgans?
No, it could happen, actually it could happen really
Because
well.
they can't recombinate with 0.
It has to be 0.
Okay.
The only genetic distance where you would say, I am absolutely sure that recombination will never happen is 0, and that's because when you calculate a 0 genetic distance, what was the calculation?
No recombinations.
Recombination fraction equals number of recombinants over total gametes. So the only way to get to 0 is if number of recombinants is equal to 0. So just by definition, you're saying we have never observed recombination between these two genes. That's what 0 genetic distance means. Even if it was 0.000001 recombination fraction, now, I mean, at least somewhere, 1 in a million kids, there had been a recombination event. Let's take the easy part first, inheritance pattern. So what does it look like at first blush? Raise your hand if you've got an answer. Raise your hand when you've figured it out. I'll give you a minute, half a minute, 15 seconds. The clock's ticking. What do you think, just from looking at this? What rule does it fit? Raise your hand. One out of 80? Sir, in the back. Okay, so dominant. Shows up in every generation. So let's see if that makes sense. If it's dominant, what alleles of which genes are responsible? So here we get back to that nomenclature. In this case, what I haven't told you is that 1 is chromosome 1, and 2 is chromosome 2. So we're looking at alleles on 2 different chromosomes. A, B, and C are genes that are on chromosome 1. And A and B are genes on chromosome 2. And then the numbers, the third character there, 5, 9, 5, 3, 4, that's size. Number of repeats of a microsatellite, for example. So that's the nomenclature we're using here. So which genes and which versions of which genes cause this phenotype? So I heard A4.
Only A4, A7, A7.
Okay, so let's just stop there for a second. 1A4. What do we need to know about this to know whether or not it's causing or whether it's likely to be causing this phenotype?
Well, the phenotype will have homozygous A5. Well, in fact, are the people who carry the disease have A4, A5, meaning that A4 is probably dominant.
So if it's dominant, what I just heard was that everybody who's unaffected, which I'm circling in red here, only have 1A5 over 1A5. They're homozygous for one allele. So the perfect correlation between a genotype and the phenotype. Everybody who has the disease has the A4, 1A4 version. Does that work? Any problems with that? Yeah?
Not a problem, just, when I was looking at, seemed to be 97.
Which one?
The 1B9 and 1B7 would follow the same patterns.
Ah, so here we have a haplotype. We have 2 genes that are next to each other. Show the same pattern. So which one is it? This is perfect correlation. When you have the disease, you have those 2 alleles of those 2 genes. You get a 1A4 and you get a 1B7. So which is it?
Is there a possibility that having just one of them doesn't make disease, or make you phenotype the disease, but having more of those?
So that's a great question. Is it possible that you have to have that combination together to get the disease? Or is it one or the other? So think about that for a second.
So this could be like both of them are affecting or like hitchhiking? Could it
Exactly.
also be?
So it could be both are necessary for the disease, or it could be that one of them causes the disease and the other one just happens to be linked. It's hitchhiking. They're always transmitted together because there's very little recombination between them. In that case, there's no way to know which one of those 2 causes the disease. It's just there's a gene in that region of that chromosome that causes the disease.
So the answer would be just explaining like, oh, it could be hitchhiking, but we don't know for sure.
The answer, so which alleles of which genes are responsible, the answer would be the pair, 1A4 and 1B7. There'd be a gene somewhere in that region, probably in between those 2 alleles, that's causing this disease. And of course, it doesn't have to actually be either of those alleles of either of those genes. It could be a gene in between them that we're not even looking at in this chart. Right? Chromosomes have thousands of genes on them. Here I'm diagramming 3 spots on one chromosome. So it could be a gene on the entire upper half of chromosome 1, the way this is diagrammed.
If you answered that on a test, and B7 or these. It could be either or both.
Yeah, you could say either or. Yep. Yeah. What sort of information could I give you? Let me see, just a second. Is there any place on here where there's a 1A4 without a 1B7? So what if, what if I did this to individual 2E? What if I made them 1A4 and filled in the symbol? Now you have evidence that it's not, that there's still a perfect correlation between phenotype and the 1A4 allele. So even just one piece of information could help you decide between the two. I just didn't give that in this example. But ultimately, that's what human geneticists or pet geneticists are looking for when they look at pedigrees of organisms to figure out what gene causes what trait. They're looking for that one individual that has separated a bunch of linked genes so that they can figure out which allele of an individual gene causes a trait.
What would happen, because you mentioned like what if it's between the A4 and the B7, unless you had A4, B7, but there was no phenotype that we were expecting, would it just mean assume it's in the middle and then we'd have to redo the genetic markers and test it?
Right, so then the question, if you want to get even more in detail, yes, absolutely. It's possible that you would have the phenotype, well, one possibility is that you could have the phenotype in an organism that has neither of those. And then everybody throws up their hands in despair. So let's say A5 over A5 and B9 over B9. And now we're all confused because now we don't have perfect correlation between the genotype and the phenotype. Now we've got a diseased individual that breaks what we thought was our rule. There could still be a gene in between those two that's causing this trait, which is why we don't have a perfect correlation anymore. I won't do anything to you like that on an exam. But in reality, that's what professional pedigree analysts have to deal with. Sometimes you're not looking at the right spot on the chromosome where there is a gene that causes a trait. Sometimes you're just looking nearby. And occasionally that sort of thing will happen. We're going to look at a sort of a related example if we get there this class in a little bit. Pedigree that defies all the rules. And I do this not to frustrate you. I understand it's probably frustrating to get these sort of ambiguities. But the point is that we learn a lot about biology by finding exceptions to rules. When everything always follows the rules, then we don't grow, we don't learn anything about the nature of biology or how genetics works. So looking at the extreme cases and exceptions is how we grow, intellectually and as a profession. Review from last time. Autosomal dominant, autosomal recessive. Did anybody, we don't have to do this. You tell me what you want to do. But I asked if anybody would come up with exceptions to the rules of autosomal recessiveness.
Under B, you just put that in one of the perspective. And normally you skip the generation, but if both of them are affected, then you wouldn't skip a generation.
Okay. So if both parents have a recessive disorder, then it's going to show up in all their kids. That's a great exception. So if you have a mom and a dad, if this is a recessive disorder, if they're both affected, we know that they're mutant over mutant and mutant over mutant. So all of their kids will be minus over minus. So then it doesn't skip a generation. Fair enough. What's another situation where a recessive disorder won't skip a generation? It's not this, but it's close. Crossing over. Yeah, if it's a polygenic trait and there's crossing over, which is not a case we've talked about yet, but that would be another exception. What if both parents aren't affected? What if one of the parents is affected and one is a carrier? Same answer. You'd have potentially some affected offspring in the following generation. It wouldn't skip a generation. If it's a recessive disorder, will every affected individual be homozygous? I want to say yes. That's the definition of it being recessive. So you have to have 2 mutant versions. So there's no exception to that rule. There's no exception to males and females being equally affected for autosomal recessive. X-linked recessive is a different story, which we'll talk about today if you want. So it's really the skipping a generation part that there are definitely some exceptions. Okay. We already looked at the Socrative quiz, but if while we're talking you find yourself yawning or nodding off and you want to be doing something a little bit more active, feel free to do this. So draw a pedigree. I just sent you a Google Classroom exercise. It's not for points. You don't have to do it. It's for an exercise, for practice. If you want to draw me a pedigree, fill in some symbols. Try to make it an X-dominant or an X-recessive inheritance pattern. Don't say what it is. Just draw a pedigree. Don't put your name on it if you don't want to. That's fine. And then attach it. And sometime closer to the end of class, maybe I'll pull up 1 or 2 of them and we can work through them and see whether or not we agree with your assessment that it's an X-dominant or X-recessive inheritance pattern. In the meantime, I'm going to keep talking. So if you want to work on that and don't want to pay attention, that's fine. As long as you don't bother other people by participating in this exam. So before I launch into other examples and while you're working on that, does anybody have any other questions about pedigree analysis, especially the topic for the day? X-linked, Y-linked, cytoplasmic. Is there anything that people felt unclear about, especially from the video? Yeah?
Are we going to be told it's a X-linked disease or just a regular autosomal?
Pardon, say that again?
So are we going to be told whether or not it's a X-linked gene or not?
You have to decide. So this is the way that these questions get posed to any geneticist. Like, we never know in advance. I'm not going to tell you in advance. I'm trying to have you do things that practicing geneticists have to deal with. So, for example, in this case, although you might remember this example from the movie, I threw this slide in my set of PowerPoint slides, and then I forgot which inheritance pattern I've been talking about. So now I have to do this from scratch. So what is the inheritance pattern that's here? You won't know in advance, basically, is the short answer to the question. You have to decide from all of the different possible inheritance patterns. In fact, let's skip to that example. What are the different inheritance patterns we've talked about? Let's list them. Autosomal dominant, autosomal recessive, and then X-dominant, X-recessive, Y-linked, cytoplasmic. So we've talked about 6 different inheritance patterns so far. And you're going to have to decide for every pedigree which one of those 6 it is. That's actually a lie. Most of the time, you won't be able to rule everything out except one. That's definitely true for this pedigree. Not enough information, I can tell just by looking at it. You're not there yet, but you will someday. One generation with 2 parents and 4 kids is not enough information to rule much out, but we can rule out. So what I'm asking you to do is not to tell me which one is right. I'm going to ask you to tell me which ones definitely cannot be this inheritance pattern. So which patterns can this not be? Can't be. Why can't it be Y-linked? Because the male doesn't have it. The dad doesn't have this disease, so it can't be Y-linked. females don't pass on Y-linked traits because females don't have Y chromosomes. Okay, anything else we can rule out? Could it be dominant? So it could either be autosomal dominant, could be X-linked dominant. Let's see, X-linked dominant. Would an X-linked dominant trait be passed from a mom to a daughter? Moms can pass X chromosomes to their daughters. What about their sons? Yes, because the sons get their only X chromosome from their mom. So that's fine, yeah, that's fine. Question? Stretching. Okay. Everybody take a stretch break. So we're left with, could it be cytoplasmic?
Yes.
What's the pattern for cytoplasmic? Mom to all of her offspring. So it could be cytoplasmic. Could be either of the dominant patterns, could be cytoplasmic. What about recessive? Let's see, let's do a quick hand raise, use that old-fashioned technology. We're gonna do between maybe and no. Maybe it could be recessive or no, it can't be recessive. So if you think it's maybe possible that it's recessive, raise your hand. Just me? And 3, okay. What about no, it can't be recessive? Okay, why can't it be recessive? I don't disagree with you until you explain why you picked that. Go ahead.
If it was recessive in order for all the offspring to have it, then dad would have to have it. The X recessive, like,
So well put. If this was X recessive, and the kids are affected, then which parents, both parents have to have the mutation. So if it's X recessive, then the dad and the mom's affected. So if this was X recessive, mom would be homozygous for the mutation. She's affected. What's the weird thing about males and X recessive traits? Males only have one X chromosome. If it's mutant, the male has the trait. This male is not affected, so we know his X chromosome is wild type. So the male is wild type over, sorry, that's a dash. Let's use asterisks for mutations. The male's hemizygous. So he's got, that's his Y chromosome, he's got no gene there, his X chromosome's got a plus. Okay. So it can't be X recessive. Could be autosomal recessive.
No,
Why not?
because all of the children, if they were heterozygous, then they would have to be, you would have a chance that they're not showing phenotype.
Okay, I'm trying to pick a fight between you. Who wants to argue the other side? Could this be, so that's a no for it can't be autosomal recessive, because all of the children, if I understand correctly, because all of the children have the phenotype. So yes, that's the other argument is what if dad's a carrier? So it's recessive, dad's a carrier, he doesn't show the phenotype, that so far is consistent with his pedigree. But then we're still left with the question of, wait, how are all the kids affected? And the response to that I heard was, maybe we haven't seen enough kids yet. Chi-square test coming up. So if here's our assumption now. This is chi-square from the ground up. Review. Our assumption or our expectation is what we're testing. So we're going to expect that the male is heterozygous, plus over minus. He's a carrier. So that's our expectation. If that's true, so we're trying to rule out autosomal recessive. If it's true that he's a carrier, is it possible that all 4 of his kids would be affected? So we've observed, we've got affected. Here are our phenotypes, 2 different categories. We've got affected and we've got not affected. We've got 4, we've observed 4 affected kids and 0 unaffected kids. Yes?
So you're saying all of the 4 kids, none of them are, it's all like they're all fully filled in? Like none of them are half and half?
That's all 4, in this pedigree, all 4 kids are affected.
So if the dad is a carrier because he only has 1 X chromosome, then wouldn't both the boys only be carriers because they only have 1 X chromosome?
Well,
But if this is, oh, sorry, this is not X chromosomes. Now we're talking autosomes.
Okay.
Autosomal recessive. So dad has 2 copies. Yeah. And we're saying that one of them is plus, one of them is asterisk. And for mom, because she's got this autosomal disease, she's asterisk over asterisk. So that's the hypothesis. That's now our expectation. What if dad's a carrier? What would our expectation be for affected versus not? 2 and 2. That's the Punnett square where dad provides either pluses or asterisks to all of his offspring, and mom gives just asterisks because she's homozygous for them. So you get 50% heterozygous offspring and 50% homozygous offspring. So that's how we get the 2 and 2. Equal ratios. If you've got 4 kids, half of them should be carriers, half of them should be affected. Right? That's a carrier. Those ones are affected. So simple chi-square test. Observed minus expected squared over expected, etc. So that's observed minus expected squared over expected plus observed minus expected squared over expected. 4 minus 2 is 2 squared is 4 divided by 2 is 2 again. 2 plus 2 equals 4. And I think we've done this chi-square test before. It comes up a lot in class for some reason. 4 kids makes the math easy. So if the chi-square value is 4, we've got 2 categories. Degrees of freedom is 2 minus 1 minus 2 minus 1 is 1. The 2 categories again being affected or unaffected. The p-value for that is 0.045. You look it up on a chi-square table or you do it in Google Sheets or Microsoft Excel or something like that. Okay, p-value. You better tell me what it means. Yeah, that'll get you some of the points. But that doesn't answer our question. Is it likely that the dad's a heterozygote? Is it possible that a heterozygote dad has 4 affected kids without having one that's just a carrier, is the question. What was our expectation again? We expected, the expectation was dad's a carrier. P-value less than 0.05 means we reject the null hypothesis or reject the expectation. So that means it's statistically unlikely that a dad that's a carrier would have 4 kids that are all affected. In other words, dad's not likely a carrier. Not likely a carrier. It doesn't mean he's not, it just means it's not very likely. The more kids we look at, the less likely it becomes, until we look at an infinite number of dad's kids, poor guy, then we'll never know for sure. So in this case, dad is not likely a carrier. And at the request of one of you after class last time, I got a request for having more practice problems for applying chi-square tests to various situations. So I'm almost done writing a separate exercise. I'll provide a key as well, with a lot of different types of questions that all involve chi-square analysis if you want to use these to practice. They're going to look something like this. Okay, I'm going to skip this for now anyway, because I want to have a chance to see if anybody sent anything from Google Classroom. Go, go, go. Let's see. I have to find one I can actually see. All right.